Hello.
Ready for you. So, okay, got the audio going again. You hear us okay?
Yeah, everything's good over here. Okay. My name is Misha Niskin, and I work at AdZerk in Durham, North Carolina, and we do all Clojure all the time. It's pretty awesome. We serve ads. Did almost 1 billion ads the other day. Alan Diapert is actually here also. We kind of perpetrated some of the crimes you're going to see tonight. So the format that I'm going to do tonight, I was hoping to maybe do a little bit of live coding and question and answer as much as possible, rather than just have a bunch of slides and kind of lecture. I think we would probably, I think that would maybe be more productive. So if anybody has any questions or anything, please at any time let me know. Okay?
Okay, we'll do.
Great. So Boot is a number of things. The simplest way to describe it is as a build tool. But a little bit more than that, it's a tool for building tools. And even more general than that, it's a bootstrapping, it's a machine for bootstrapping a Clojure application. So I think the concept of bootstrapping is something that isn't really handled very much in currently, and I think I would really like to kind of talk a little bit about that first. So what I mean by bootstrapping is really what we want to do. Most of the time, what we want to do is concerning applications. Like we make libraries, we put them in jar files, we deploy jar files to Maven. But really what we want to do is we want to run applications, and all these other things kind of serve that purpose. And so what do we need to do to get Clojure to actually run a program? So we need to do a number of things. We need to set up the immutable class path, meaning the jar files, the things that you cannot change at runtime. So you need to get jar files ready for your program to use. There's also sort of a mutable class path as well, which is directories that you add to class loaders. And those could contain files that could change at runtime. So there's a mutable class path as well. And then there's an environment. These are like top-level vars, things like that, that need to be in place before your program can run and do its work. So those are the three main things that you need to bootstrap a Clojure program. This is what you need to get a Clojure program to run. And I mean, the final step after you've done those three things is you launch your program in such a way that, using the whatever the calling convention is for your application. You have some entry point and some way that you call it. And so those three steps plus the final step of launching is sort of like the interface with the platform. And we want to be able to write applications that aren't tied to a particular platform. We want to be able to write applications that can run, in a testing environment, and we could deploy them to Beanstalk, all kinds of things. And so that's really what Boot came out of, is that, the way we build applications and the way we deploy them is so much richer now, and it's getting richer every day, like the things with AWS and Beanstalk recently. We're doing so much more with our applications, and the tools they just can't keep up. So when you look at, most build tools have some kind of declarative configuration. So like a giant map with a bunch of things in it that describe how the build tool should do it. And this, does not scale to the things we need. Like now we need asset pipelines. We have all kinds of integrations that need to happen before, your application can run or be built. And the way that people have been solving this up till now has been, just generating reams of boilerplate. So you have some kind of task some kind of template system that will spit out all these configuration maps and scripts and all kinds of things. When really what we need is we need to write a program that builds our program. We need control. We need to be able to do new things with our tools. And we need to be able to abstract over that. We need to be able to make modular components that we can use, to build our applications modularly and to provide, the substrate that we need to be able to make applications that can run in different environments. And so I think there's a little bit of a myth with like immutability and maps and declarative that has been going on that's really kind of been holding us back. So people look at like a Leiningen project.clj file and they say, oh, this is a declarative, representation of my build. But it might be declarative and it might not. I don't know exactly what that word means, but it's definitely not good, because when you look in there, like, everything is global. You have a bunch of names. So you have keys and values. Those keys and names, and they're all global. And tasks, different plugins and different things inside of there are communicating via those things, but they're all global. There's no scope. There's no control flow. There's no, there's no way for the user to express an intent that hasn't been foreseen by the people who wrote the parts that you're using. And so what you end up seeing is, if you look at any of the ambitious things that are implemented in Leiningen, like Figwheel, and there's a number of them, and the one thing that they all have in common is that they have to do everything. They all implement every single part of the monolithically. No parts are reusable, no parts are composable. Somebody might have a really good implementation for like live reload, which is, you're doing something locally, and it sends a message to the browser to reload some part of its stuff because you changed something. There's no reusable way to do that. Everybody has to re-implement it, and how you call the compiler, all these things. So Boot solves these problems. So I think maybe we should get started. I don't know if you guys downloaded the Boot binaries yet, but you could go to bootclj.com. and that will lead you to the GitHub where you can download binaries and install them. So I will type it into the window here. I hope you can see it. That is our URL, and we're on GitHub as that is the GitHub repo. Boot is open source. It's EPL, same as Clojure. You can fork it. You can do whatever you want. You can download the binaries. Everything's EPL. So I'm going to show some basic stuff. Once you have Boot installed, I'm going to show some basic things that you can do. So let me share my screen. So this is the boot command. The executable will run. It's an executable jar file, basically. And there's like a Windows version too. Maybe I can do. How's that?
That's fine.
Okay, so I just typed in boot, and this gives us some help information that'll be useful if you use boot. So it tells you, like, these are the first things are the options to boot itself. So that tells boot like how to run. And then what follows are a bunch of tasks that are built into boot from the get-go. So these are tasks that you can call kind of like in Leiningen. So you can see like jar, AOT, Java, whatever, all these things. And then there's some environment variables that tell boot how to run also. Okay, so now let's say we want to get help for a specific task. So there was a REPL task, so we could do boot REPL -H. So you give it options, kind of like in like Unix type options. And you see help. So this tells you all the options for that specific task. An interesting thing about boot also is that all of these tasks are actually Clojure functions that you can call in the REPL. So if we were to start a REPL now, you call them differently from the REPL, but we could do, remember, we're the REPL task, and this gives us help with, like when you're in the REPL, when you're in Clojure, you express the options as keyword arguments. So here we have, you know, here we have the keyword arguments. Okay. So the first section of the demo is how to get help about things in boot, and that's how you do it. Second part is boot consists of this executable that we ran, and what that does is that's just like a minimal shim to get enough of a Java environment working that I can launch some pomegranate stuff which pulls in dependencies from Maven. And all of the actual boot logic exists in as jar dependencies that it pulls in dynamically. So we can change the version of boot without changing this binary at all. In other words, we just depend on a different version of the actual core jars that implement all of the boot functionality. So boot is this executable, and then it's the things that it loads with Maven. The third thing is, what do you do once you have boot running? So the convention for boot is there's a file called build.boot in the current directory which tells boot what to do. Boot can also be used with a shebang style, you know, to write like one-off scripts that can pull in dependencies. But for now, let's just talk about using it like a build tool. And so there's this build.boot file that tells boot what to do. It's kind of like project.clj, but it's a program that runs. It's not a configuration map. It's an actual program that runs, that boot will run for you. So let me go to my. So I started preparing a little demo here, but I'm gonna actually blow things away and okay, yeah. So I have basically an empty directory here with a build.boot file. The build.boot file tells boot what to do. So currently, right now, I'm just telling it where, which directories source code will live in. So that's what I'm doing here. There's this this function setenv-bang, which sets up the environment. So this is basically setting up the things that we need to be able to run our program that will do the building, if that makes any sense. So the purpose, what we're trying to accomplish here is we're making a program to build our project rather than, you know, a configuration map. So in order to run our program, we need certain things to be in place. We need to be bootstrapped just so that we can run the Clojure code that will build our program. So the first thing that I'm doing is I'm saying, okay, I'm going to have some source code, and it's going to be in these directories, src and task. We'll see why I have two of them in a second. So let me make those directories. Now this is what we have. So now let's do something with the build.boot. I'll show you a task. So tasks are the first. There's three core concepts in boot. The first one is tasks. The second one is the file set, which is how boot uses an immutable abstraction over file set operations. So there's tasks, file sets, and pods. Pods are an isolated class loader mechanism that allows you to evaluate code in a class loader that has different dependencies than the current environment. So this is really useful to avoid getting into like dependency hell when you have, you know, conflicting dependencies for different orthogonal activities. So tasks, file sets, and pods. I'm going to make a task now. We can do this right in the build.boot file, no problem. Tasks are defined with a macro called def task. And the deftask macro has a form very similar to the defun macro, which is how you define a function, a named function enclosure. So we're going to define a named task. And tasks are actually functions, but they're special in certain ways. So we're going to call our task foo, and it will take no arguments, and it will basically just print hello world. Okay. So what's happening here? Oh, sorry, was there a question?
Next hand.
Next handler is next.
Oh, thank you. Yeah. Sweet. Okay, so I'll save this file and then we'll just run it real quick. I could do boot again, and we will see that this task now shows up over here. So we could do boot foo that prints hello world. We could do boot foo, foo, foo. It's 3 times. What's going on here? Well, boot tasks are kind of like, we used to describe them as, we used to call them middleware factories, but Rich Hickey has a cool word for them, which is stateful transducers. Sounds way awesomer. And basically what they are is, if you think of, I don't know if you guys have experience with the Ring web framework, but Ring operates similar to Rack, I think, as well in Ruby. And this concept of middleware, where you have a function that takes as its argument a continuation, sort of, and it returns a function. So here we have this middleware function, which is what the task foo returns. And that's a function that can take a handler, which is what the middleware returns. And the contract is that the handler needs to call the next handler with some argument and return the result of that. So it's very similar to Ring. Ring middleware, basically the file set would be a request map, and this result would be a response map, which would be passed up the handler stack. So are you guys familiar with Ring?
Yep.
Okay, great. So what this means is that we could do something cool. We could define a new task that is the composition of other tasks. So if we now run boot bar.
I think you had a typo.
Oh, man.
Deftask.
A little bit nervous, I guess. Okay. So what I'm demonstrating here is that we can make a new task, which is a composition of tasks that exist. And we do it very simply, just using the regular function composition. And this is pretty powerful because we didn't show it here, but this is stateful. So we could do something like this. What I'm doing here is I'm allowing foo to take an argument, and we'll do let actually, let me make this an integer. And I could do Okay, so okay, so what are we doing here? I define a task called foo. It takes an argument. I'll explain it. This is like kind of a little DSL for making arguments that work on both the command line or from the REPL. So, but basically it's taking this argument arg, which will be parsed as an integer, and we have an atom here, which contains, its initial value is arg, but every time this task gets called, it's going to increment the state. So this is a stateful task, right? And this is important because we're going to want to be doing things like caching things and whatnot in task later. So and bar is going to create two of these, but with different initial states. And so I can do something like this, like boot foo minus a 17. And then I could do boot watch foo minus a 17. So what I just did was I started a file watcher that's watching our source paths, our source directories, and then there were no files in it, so it didn't do anything. But then when I created a file, it ran the task. So if I update the modification time of that guy, it ran the task again, but you can see it kept its state in there. This is what's running. It ran twice. Each time the handler was called, it incremented the state. So it ran twice, so it was 18, now it's 19. And if we run it again, it'll be 20. So what's actually going on here? This watch task is a completely general task that watches the source directories and it calls its continuation whenever they change. So it keeps a reference to the continuation, to the next handler, basically, and it keeps its own state, meaning it knows what the modification times are of files and things like that. And whenever it gets a file system event notification that something changed, it can call the rest of the pipeline again, which is, like, I think pretty powerful, because that abstracts away that entire, that's doing flow control, it's doing a lot of things. So tasks are stateful transducers. The state is every task basically sort of has this general format where you take some arguments or whatever, you make some state that your task will have, and then you return a middleware. Middleware is a function that takes the next handler as its argument and returns a handler. The handler is a function that takes a file set and returns a file set by way of calling the next handler. So there is a macro in boot that allows us to simplify this.
I have a question.
Sure, yes, please.
So do the names of those functions have any meaning, or you just put them in there for clarity?
I'm sorry, I'm having a hard time hearing you.
I'm in the back. Are the names of the functions, do they have any meaning in boot in general, or is it just for clarity?
You mean like middleware and handler?
Yeah, exactly.
No, I just put that's totally optional. I just put that in to sort of illustrate what they were doing.
That's okay. Thank you.
Yeah, this would work too. I just put them in there so that it would be a little bit easier to see what was going on. So we actually there's actually a little macro that we can use that will save us from a lot of this stuff. So we could do. So this is actually equivalent to what we had a second ago. So what with prewrap does is it's just a macro that constructs all those functions, because most of the time what you want to do is you just want to do some processing for side effects or whatever, create some files, and then you want to add them to this file set object. So right now we're not modifying any files, so we're not doing that, but basically this simplifies that, so we don't have to deal with all those anonymous functions. Is everybody cool with that? Cool. Okay. So this basically does the work before calling the next handler. There's also with post-wrap that does the work after calling the next handler. So now let's actually start. Let's make a task to compile something. And a simple thing that I think we might want to do is, like, say we have files that end in like .lc, meaning they're like lowercase files, and we're going to convert them to .uc, which is uppercase files, by making any lowercase file characters in them to be uppercase. So it's a demonstration of kind of like a typical compilation type task that we can do. So the first thing maybe I'll do is let's define some functions. Actually, I'm going to start up a REPL, and we'll do some development in the REPL, which is fun. This command is doing is it's starting a REPL, just a REPL server, and then it's calling this wait task, which just tells it not to exit, because the REPL server isn't going to block. So basically, we're just starting a REPL server so I can connect from Vi. And now I will do I'll call the task upper. And we'll require some things. Okay, got that, and we will do same as before. We're going to do first thing we're going to do in our task is we're going to set up some state, and the state that we actually need for this task is we need a temporary directory in which to emit the files that the artifacts that we compile. In other words, the result of compiling our stuff, it has to go into a temporary directory. And a fundamental thing with boot is that tasks don't know what happens to things that they produce. They don't know. Like, no task knows where the target directory is, like where on the file system things will end up in the end. All they can do is create a temporary directory of their own that's anonymous and just scoped to them, put files into it, and then add those files to this file set object to be passed down to the next thing. So no task knows whether the files that it creates are intermediate objects or final ones. It doesn't know if something will further process them, maybe delete them later, who knows. So that means that the first thing we need to do is obtain a place for us to put the files we compile. So boot provides a facility for managed temporary directories. In other words, these are temporary directories that boot takes care of cleanup for you. So there's never any stale files, ever, in boot. So there's no clean task. There's no boot clean. It doesn't exist. So we create this temporary directory with this tempr_bang function. And here, since we might be called multiple times from the REPL, or there might be a watcher or some other thing that's calling my task multiple times, I want to make sure that this temporary directory is clean before I do any work. So inside of my task, so this with pre-wrap, this contains the actual work that's going to be done, the code that I'm going to run in the task. And so the first thing I'm going to do is empty it. So that ensures that before I do any work, I don't have any stale files in there. And then the next thing I'm going to do is I will call, I will get a list. So first thing we want to do is just get a list of all the .lc files that are here, that are present. So I will explain what this is in just a second. Actually, I should have done a different thing. I want an actual REPL here too sometimes. Okay. So now I could do so I could do this. I could call the task from here. Okay. And now I will make a .lc file. So okay, so I made a file and I called our task, and our task printed this file. So you can see that the file is in like a temporary directory. It's a weird thing. So this is actually a thing that represents a file, but it's an immutable object that represents this file. When we need the contents of it, we'll be able to get them later, but the file set is like representing a point in time, the file set at a point in time. It has all the metadata about it, including the contents, kind of like Git. So we have a blob storage area where we use content addressed, we use content-based addressing. So this object gives us all the information we need to recreate this file in the place where it was when that file set was created, when the immutable thing was created. So that means that if you have this immutable file set object, you can pass it around and somebody else can recreate the file system exactly how it was when that file set object was created. This gives us the power to deal with the file system in a somewhat immutable way. In other words, things can hold references to the file system, to a snapshot of the file system, which is really handy. And so that's kind of what we're demonstrating here. We're looping through, so the file set, it contains a bunch of files. And files are basically in two different categories. Input files, which are things that could be compiled, and output files, which are things that will be packaged for deployment. So right now we're going to compile things, so we're interested in files that are meant to be compiled, that are intermediate or source files. So we use this input files function to get them. And this function just gets the ones with the .lc file extension. So, and then we loop over them doing a side effect. So instead of that side effect, we could actually have. Did that make sense? Are people okay? Hello? I think we might be disconnected.
Said it crashed. Oh, there we go.
Oh, crash. Okay. I think we're back on the air.
Okay.
Oh.
Okay. Did that make sense? Did you get the stuff about the file sets and what they do? Are we?
Yeah. Yep.
Okay. Okay, great. So we can make a task now. Sorry, a function that would be like I'll see. Takes, so here we have a function that takes like basically the input file, the lowercase file, and where it should compile the uppercase file to, and it would be LC file slurp to case. Okay, so that's a pretty simple function. All it does is take a file, make everything uppercase, and write that to another file. And then we will modify this guy to define some things. Remember what we got. Remember the thing we printed out wasn't an actual file. It was like this. It was this record that represents the file. So this temp file function is how you get the an actual file out of that. So there is a file in the file system with those contents, and we're going to need that. But it's kind of an anonymous thing. You'll see that like our task won't even care about where it really is. We just need a handle to that file. We do care about the path relative to the class path. So this is like a relative path relative to our source directory in this case, and we care about that. So we want that, and then from that we can make our where we're going to emit to. We're going to emit to so basically we're making a file in our temporary directory that has the same path relative to that directory as the source file is to the source directory. Actually, we're going to need to do one more thing. So let's do let's see. Basically what this function is doing is it's just taking a path and replacing the file extension with .uc, replacing the LC file extension with UC. We're going to use that here. And here we're going to compile. See. And debug, I'm going to do it. Now let's run this from the REPL again. Oh, slurp. So this is just to debug, just to debug. So I ran the task, and it actually compiled our file, and we can see the output. But there is one more thing we have to do to make our compile task work, and that is we have to add it to the file set. And let's actually see what happens now when we run it. Boot, what was it? Upper. Oh, right. Yes, we need to adjust our build.boot because being a program, we need to require the namespace. Now we should be able to do it. So it didn't actually make any files. It didn't produce any files. And the reason why it didn't produce any files is because we're getting the file set and we're just returning the same file set. So what we need to do is add the files that we just compiled to the file set. So what we're going to do here is and then so this is very similar to Git. With Git, you can add files to a change set, stage them basically. So here we stage all the files that are in this directory to our file set, and that actually returns a new immutable file set. It doesn't modify the existing one. And then we call commit bang on it, which persists that to the file system. So that makes the file system like the file set object, and it returns it. So this whole expression evaluates to the file set that has these temporary files in it. So when we do this guy, oh, of course, EOF while reading. That means something not maybe balanced. Yeah. Thanks, bye. So now there's a target directory in there. And you see the target directory has foo.uc in it. This guy. This is the product of compiling this guy. And so we could do and we could see that it did its work. So we can now combine that with other tasks. So we could do like boot watch upper over here. And then we can go over here and do oh. Really? Oh, all right, yeah, that was something weird, but yeah, there we go. So every time I can recompiling the thing. What else? Okay, so this is a basic. This is kind of a typical task. You guys have any questions?
No questions so far?
What's that?
I don't see any questions here.
Okay. So one of the things that we could do is to gain efficiency, because here we're basically rebuilding everything every iteration. So every single .lc file gets built anew each time. So maybe we don't want to do that. Maybe we want to only rebuild ones that have changed, and we could do that by making by adding some more state. And because the file set is immutable, we have a lot of power to do things like make diffs and things, just like in Git. So we're going to leverage that immutability now and only look at the ones that have changed since the last time we ran. So I will do here. File set diff we think about, yes. So the file set diff function, it takes two file sets and it returns a file set. Oh, actually, sorry, I did this in the wrong place. The file set diff function takes two file sets and returns a new file set, which is only the modified files, which contains only the modified files. And so basically, there we go. We got that. And so now what we need to do is, now that we've done that, we need to make sure that we reset our state. So after we compile, we need to tell it about the, we need to reset our state to the current thing. So we could do this. And actually, let's print some debugging information telling us what files are being compiled. This again. Oh, right. Sorry, I had a bug. I want the actual file set that's contained in there, not the atom itself. So now let's do now we can see I just made this other file. It didn't recompile foo again. It only compiled bar. Now it should compile both of them. Oh, it didn't actually it didn't compile any of them because it's looking for their content, not their modification times. So what we have to do is, man, we can't atomically. Yeah, it'll be hard to do it, but it's yeah. So but here I'm just adding some content to those guys. And it compiled both of them. So this is showing how tasks can manage their own dependencies. So, and this is like a pretty big thing because most build tools have a directed acyclic graph. They have some kind of dependency graph like that determines when tasks need to run by some central authority. So if the central authority, like you tell the central authority, I depend on .lc files, and then the central authorities, looks to see whether these files have changed and calls me or not, depending on that. But this is actually a lot more powerful because we have, we're controlling it inside of our task. So now no other things need to know whether this task should run or not. Boot just runs everything, and the task itself decides whether it does work or not, which is really powerful. It simplifies things considerably. This task compiles some files. We could also make a task that doesn't compile things, that's just there for like flow control. And so something we could do is times actually, rather than that, maybe we could talk about pods real quick, and then I'm actually over time, so do you guys want me to continue, or?
I'd like to hear about pods.
Yeah.
Okay, sweet. So pods are kind of cool. And look at them in the REPL. The main deal is the main purpose of pods is to give you a first-class abstraction, a first-class object that is basically a Clojure runtime that's completely isolated from the Clojure runtime that your code is evaluating in. And the utility of this is that you can avoid dependency hell because you have all these, you're doing all these different things, and a lot of them have hairy dependencies. You know, like the ClojureScript compiler has dependencies which, you know, end up pulling in like Apache HTTP client libraries and things like that that will then conflict with, you know, logging libraries, and you know, you have the whole Datomic SFL4J thing. And so to solve this problem, we developed these pods. And what we could do is, so I could do this is just a dependency that I don't have installed right now, so I get an exception. But I can make a pod. So P1. Oh, I have to import another namespace. 1 second. They're in the boot.pod namespace. Then so there's a function makePod which will create a pod, and it takes one argument, which is an environment. And this environment is basically the environment that we used with setenv before. It's like the dependencies and the directories, all the things you need to set up the class path for this pod. So right now we'll give it the same class path that we have. So we'll give it the same environment that we have in our current thing, but it'll be a separate Clojure runtime. So I used the getenv function here, which basically returns the environment. So you can see it has our dependencies and, you know, directories and repositories and all kinds of things. So now I can evaluate code in P1. So I'll do pod with eval in P1. And I don't know if you can see this, but it says 2. I'll also do fire. But or we could take values from the current runtime and use them in our expression that we're going to evaluate in the other one. So I could do def x 100, and then we could do pod with eval in p1 plus 1. So this tilde here, basically this is a template. The expression, the body of with eval in, the body expressions here are basically templates like Brandon Bloom's backtick library. They actually use that. So basically it's like syntax quoting, but without the symbol resolution. So it just does the unquoting, you know, the templating. So here I'm adding 1 plus x, and I'm taking x from the parent environment and bringing it down into the pod. And then when I'm done with it, I could do, and that's pretty important because you want to make sure that, because pods take up about 12 megs of memory, so if you can create them anonymously, use them, destroy them, and then make a new pod later, which we do a lot. And this is amazing because it allows us to actually run things in anonymous, lexically scoped runtimes. Like a Clojure runtime that's lexically scoped and maybe even anonymous and basically you could pass around a function that does its work in another Clojure runtime. So, and we do this for we have a logging library that basically solves the Datomic SFL4J problem by doing all the logging in a pod. So your application actually has no implementation, no dependency on any logging implementation. It's only the pod that does. So I'm going to demonstrate that. So we did over here, I tried to require a namespace that is not on the class path. And now I will make a pod that has that namespace on the class path. So first I'm going to create the environment. I'm going to define the environment that that pod will be created with. I'm going to add a dependency. I'm going to conj onto the dependencies. It's not supported. Oh, sorry. I always do this. Needs to be a. There we go. Now if I do this is very similar to what you do in Linigan for dependencies, by the way. So now we're seeing the dependencies that the pod will be loaded with. And if we look at our current dependencies, we see we have none in the current pod in the REPL here. So now I'll do so now I could do this require that failed here. I could do it in the pod. And it succeeds. Actually, we could do I do with try to think of a thing that's going to be in there. We got NS publics. Right, so I just ran in the pod. This shows us all the things that are in that namespace that I couldn't do in my current environment. I tried this in the current environment, it would fail. But in the pod, it works fine. So with task, a lot of times, this is actually how we do tasks. So like the ClojureScript compiler task, for example, or whatever, we would normally do something like this. So instead of actually compiling in this process, what we would do is over here, we would create a pod. Actually, I have to and then over here, I would do so normally we would add dependencies here, but for now, because we don't really need them, I'll leave that out. But basically, where getenv is here, we would be modifying this to have different dependencies or different source directories or whatever. So we have this pod now, and then we would make a new namespace. So here we make like an implementation namespace, and this namespace is only meant to be used in the pod where those dependencies are loaded. It's not meant to be used in the rest of your program. And we will define this in there. Okay, so here we have a function that's in this other namespace, and this is what we'll run in the pod, and it has this compile function that takes the path to a file, the input file, and the path to the output file. And then over here, what we will do is we will actually there was a bug here. Okay, so what did we do here? Basically, I'm running this compile LC function in the pod now. Hopefully this will work. Cool, it compiled all the things. Okay. Here's where the pod is doing its work. And what we could have done in the so what we could have done in this file, this is our implementation, we could have been using things that have like all kinds of crazy dependencies, and we just add those dependencies to the pod and not to the rest of our program. Cool, right? What else would you guys like to see? Would you like to see like a control type task?
What's that?
That's a yes.
Okay. Or actually, maybe I'll go over the task, the options DSL, the crazy little DSL we have, a little bit. So one of the requirements for boot is that you should be able to compose tasks on the command line or in the REPL, and it should work. You should have the full functionality in both places. So over here, when we ran our command line here, these are actually two tasks that are being combined, and we can add another task. So there's the speak task, which makes a noise when it compiles something, which is nice if you have something running in the background, like recompiling, and you change a file. It's nice to hear that it does what what it was supposed to do. So there's a theme option for it, and the theme that we will use is ordnance. I don't know if you guys could hear that, but it made a little noise just now.
We heard it.
Sweet. So I could do this also from the REPL. So the command line, what I did on the command line is this. Boot, and you could also, if you want, put these in. Doesn't hurt anything. Just so you could see like where the one task begins and the other ends. So it parses out these options, and it knows which task goes with which option. So I could do boot REPL now, and I could do the same thing but from the REPL. I use the boot macro for that, and then it's just the same as on the command line, but we're actually calling closure functions now directly. So watch, speak, theme. Yeah. And you press Control C, Oh, it's interesting. I think maybe some output wasn't being flushed because we're using printf. So yeah, let me fix that actually. Instead of using printf, there is actually a thing for that. And so what we'll do is okay. So what's interesting to note here is the correspondence between the command line options to the tasks and the keyword arguments to the task functions in the REPL. And this is really key because sometimes you want to compose these things, programmatically. And so this shows us the keyword argument. So you can see over here, they're actually typed because we need to be able to parse them from the command line, which is everything is a string, and make them to be whatever closure type that keyword argument needs to be. So we can see the theme is a string. So if I were to do something like this, like maybe put a keyword by mistake, it'll actually tell us that theme must be of type str. And this kind of eases the pain of dealing with both the command line and the REPL at the same time, because it'll kind of tell you what things need to be. So if we look at the source of that, never mind. I'll just explain over here. Very similar to it's like a combination of Herbert and tools.cli. And incidentally, a task that does nothing, you can just use closure core identity. And that produces just like kind of a no-op task that can be composed with anything, but doesn't actually do anything itself. So some of the options that we could do is, the DSL, the first thing is the short option. The second thing is the long option, which also corresponds to what it will be bound to in the body of the task and the keyword argument. So, and then if it takes an argument, there's an optarg over here. So some things like if it's a flag, it wouldn't have this. But if it's a thing that takes an argument, then you put in the optarg there. And then the type. So we can make this a keyword, for example. And then a description, the demo option. So now I could go back to what was it? Okay, so the keyword arg is the demo there, and if I did this is just a little. So this is what you would see for the command line options. So C minus D, and then the long form is demo. It takes an option. It takes an argument, and it says set the demo option to optarg. Here we have demo is the keyword. It's a type keyword, and it says just the demo option. You can do more fancy things too. Like we can make another option. Like let's say we want to do like maybe properties. I'll just call it props there. But so we have properties that are like key value pairs that we want to have in a map. So we could do example, and then we tell it we want a map of keyword to string, say. Now when we go back into the REPL, so check it out. The props over here, so that's splitting it on the colon. Basically any non alpha characters in the optarg, it tells it to split that. And then it conjugates those onto the map because we told it that it was a map of keywords to strings, keyword arguments and strings. So we can now do something like, we can now do, from the command line, boot options minus P oh, actually we need to change something here. I'm going to do I'm just debugging, I'm just printing out what the value of that is. So now I will call it, oh, of course. What is wrong? I don't know how to do what? Oops, good thing. Good. Oh, sorry. There we go. Thank you. Okay. Props must be a type. Oh, yeah. So I was supposed to do foo colon bar. So here we have, this is telling us that the minus P option would be key and val separated by colon, and that gets conged onto the map. So when we did this, we get a map that has a foo key and a bar val, but we could also do it again, minus P as or we could change this to, you know, something like that, and then or we could make this a set of believe this will work. Yeah, so that's like a set of vector pairs. I mean, it's not like a full it's not a full fully featured schema language, but it's enough to do things that you would conceivably be able to do on the command line. So I mean, this is about as complicated as it gets. But basically, it's a little DSL for expressing how to parse those things into Clojure from the command line. So that's those.
We're going to show a validation failure of the properties if you enter an illegal key value table.
Right. So the purpose of the validation is because, like, I know how I want to parse this from the command line, right? So I told it how to do that here. But then when somebody's using it from the REPL, it might be hard for them to know exactly what type I need for this, you know, for this option to be. So the only time you'll see that error is when you're running it from the REPL. So let me start the REPL here, and I just do boot options. I get nil. That's good. And then props. Cool. So that's okay too. Now if I do like maybe a symbol.
Yeah. Cool.
Oh, actually, you know what? That's not right. It should have. This shouldn't have been. Huh. This shouldn't have worked. It should have had to be this. So we found a bug today. I'm going to write it down. But that's kind of a weird case. I mean, most of the time you don't have things that are that complicated. Most of the time you want like an integer, like, you know, you have your like, you know, something like that. And you just want to make sure that it's going to be an integer. Maybe the last thing we could do is make a control task real quick. So, and that'll be an example of like how to use a task to actually control the way other tasks are called, which is pretty powerful. That's how we made the watch task. But like you could imagine, of course, tasks that do other things. Like Brendan Bloom, he was talking about making a task that or not a task, but he was saying like instead of rebuilding your project when a source file changes, maybe you want to rebuild the project when you reload the browser instead, so that you're maybe working in the REPL all the time and saving your file without rebuilding anything, And then when you want to rebuild, you'll just like refresh your browser, and that'll cause ClojureScript to be recompiled. So we can make a task kind of like that. That's totally separate. So like in Lonigan currently with Figwheel or whatever, you'd have to like rebuild Figwheel from the bottom up because everything is like monolithic and one thing. Here we can actually make a task that does that, that doesn't disturb any of the other things, because none of the other things know that they're being watched by the watch task. They just run. Maybe we'll make a task that does something like n times. We'll call our task n times, and it will take an argument, n, or t for times, and that will be an integer. Okay. And our task will be
We're not using pre-wrap.
no, because with this task actually we don't want to call the next handler and then return the result back up the chain. So here what we're doing is we're actually like kind of co-opting, we're taking control of the pipeline and we're never returning. So we're gonna hold on to the next handler and we're gonna call it as many times as we want or do things with it other than just calling it that one time and then returning the result. Does that make sense?
Yeah.
Yeah, so maybe what we could do is, now my Clojure's a little bit rusty here. What do times?
Yeah. You just want to call it 2 times.
And that takes, the first thing is a number, right?
The binding. So it takes a binding vector. So
Oh, to I?
underscore
Yeah, binding.
and times.
Sweet. Oops.
That returns the file.
Yeah.
You just return the file set, I guess.
Yeah, we could. I mean, this is just, I guess, for a demo, so we could make it better in a second.
Echo there.
Okay, so now maybe I could do like boot. So there's this show task that does a number of things. Like it'll show you your dependencies or whatever. So I just use it sometimes when I just need a task that shows me that it did something, but I don't really care what it does. So might be hard to see, but it did it 2 times, of course. So what's interesting though is that we can now do like actually I need to modify. Need to modify this task a little bit to I just want to, I'm modifying the upper task to just print that it's running, but a lot of times it won't do anything if nothing's changed, but we just want to know right now that it's running because we're going to show this. Oh, whoops. There we go. So upper task actually ran twice. The first time it compiled some stuff, and then it didn't, you know. And so now if I you could see upper task ran twice again. So we've actually composed two different control tasks together now, which is, you could probably see how this could get pretty powerful. And we did it all from the command line, which is cool. But when we get things settled down more in our in our workflow, we might do like def task dev, which would encapsulate what I just did on the command line. So it would be, I want to compose watch and speak n times so now I could just do boot dev. And I could even do like, I could compose that with other things too. So I could do like boot show minus E, which will print that stuff, and then run dev. So it'll only show the thing once. And so if I notice how it doesn't print that closure map, that Eden map, because it ran before the watch task. So the watch task was kind of, that's where it's calling the continuation. It's not calling the show code anymore. But if we wanted it to run every time, we could put it over here. And now you can see it actually does it. It does it twice because we're doing do times on the rest. On that handler. Oh, and there's also a way that you could do like so suppose you want to basically curry the tasks. So these tasks are functions that take keyword arguments. They take no positional arguments. So you can curry them, and so sometimes you want to do that, which it might make, because you have some options that you don't want to keep typing in over and over again in different, you might compose them in different ways, but the options are the same. So we could do like, so for the speak task, and we could do and then we don't have to add any arguments here anymore. So I added these task options here. And what this is actually doing is it's making a curried version of these functions and then altering the var root. So these are actually first-class things. It's actually taking the var behind speak and making a curried function and replacing it with that. We could also do something like this. So you can see that it does the same thing. And what you could do is you could also update the options. So if you give it a function here, you could do like inc 0. Do I need to use fno with inc? I do.
Yeah.
Yeah. Actually, so. Oh, actually, I probably want to do no. know. What did I do? Dude, I have no idea. It's something in Tmux. Thank you. Maybe this was ill-advised. See, plus 4% 0. Oh, sorry. Sorry, the argument this thing gets is the map of options. Actually, we want to do yes, so it did it. Okay. Yeah, so this task options thing is just a way for you to, you know, kind of set those options. But you can actually, an interesting thing is that if you were to do like, you can override them on the command line if you want or whatever. Or like, if we do here, times 3, that will override the task options. And it'll do it 3 times. I think we covered a lot of it. There's not much more to boot than this.
Well, let's play.
Yeah.
Does anybody have questions?
So the task options are global for that whole file? Is that correct, sir? For any task?
Sorry?
Question, are the task options global to the whole file? Or maybe to the
They
file?
are. Yeah, they are. They're actually altering the var root. So they're working on global, you know, on vars that are in a namespace. So yeah, they're because those are like global names that you want to configure, sort of. You know what I mean? That's kind of a decoupled way that you can, you know, because you can make a function that configures tasks like that, you know. So it allows you to decouple some things.
So an immediate analogy comes to mind with the Java world, where Leiningen is kind of like Maven. It's static. It's simple for simple things, but really difficult for complex things. And then you have Gradle, which gives you a lot more power. But this is in that latter camp. I was wondering, and it seems to be sort of like a Swiss Army knife of productivity. Do you use this for in all kinds of automation and scripting tasks in your build world? And what kinds of things have you found it particularly useful for?
Yeah, Alan, actually, maybe could you talk about that?
Sure. Yeah, so I mean, Gradle, Swiss Army knife are definitely good. Similar concepts, I guess. There are a handful of things that you need to do if you're a Clojure programmer that are like Java things that you never really want to do, but you know how to do. Like you don't want to learn how to, you know, package and zip a jar file. You don't want to know how to. There's just loads and loads of things, and I think Leiningen got popular quickly because it did those things that nobody really cared to learn or relearn. like making an Uber jar or setting up a web.inf or whatever craziness you need to do. So those tasks come up a lot, I think, in the course of working on the JVM closure in particular. And with Boot, it's easier to parameterize those things than it is with a tool like Maven or Leiningen. So what that does is that gives us higher flexibility as far as the shape of our deployment. Like, for instance, it's really popular in Clojure world to use Leiningen to create Uber jars, and you send the Uber jars to Heroku or to a servlet container like Tomcat. Excuse me. But that world, that's sort of how you deploy Java apps 5-10 years ago, and us being, forward-thinking, functional, immutable Clojure people, we're always looking for the new, better, cool ways to deploy things. And one such cool way is with Docker. And unfortunately, a lot of Java tooling is kind of at odds with the Docker methodology, and some really interesting things are happening in deployment in non-Java worlds, like with Python and Rails. So one interesting way that we're using Boot is as a way to composite apps and basically shape Clojure applications into packages that are suitable for deployment with Docker. And in fact, here at work, we deploy to Amazon Elastic Beanstalk their Docker stack. Basically, they support a kind of Docker deployment. We've written a bunch of libraries that support doing that kind of deployment from our Clojure web apps. So we have Clojure web apps and Clojure worker apps that we deploy that way.
Yeah, you've been doing a bunch of stuff too, though. Like you had, I don't know, Alan was like compiling something yesterday, and it was like in the watcher loop with running the tests and installing it locally to Maven automatically if the test passed, but if not, then it was playing a sound.
Yeah, so I've definitely discovered workflows that I didn't even consider before having the flexibility that Boot offered. And this sounds like an infomercial, by the way. It looks like one even. But whatever.
Fiat now, you get this free paintbrush.
But yeah, so I've discovered these new ways. One cool thing is we had no way to run Clojure.test. That's one nice thing you get with Leiningen is you can do line test, and it has a always bare bones configuration. We didn't have that. We had to make that, but now we have a task that does it, composes it with other tasks. So
does it in a pod.
Does it in a pod, so it runs your tests in a class path, sort of inspired by, but not interfering with your project class path. So then you can, because we already had watch, that means you could do watcher-based testing, line watch tests. So then, we were doing some TDD. And then we thought, man, wouldn't it be cool if we, every time the test passed, we pushed a snapshot? It's like, okay, so then every time the test passed, we'll make a cool noise, build a snapshot, and push it to our Maven repo. It's like, okay, what other neat things do we want to do? Because you can, you have this flow control ability with tasks. So I think we're really just starting to get into the new kinds of workflows that are possible, because it wasn't until probably within the past 6 months that we had all the Java bits that were uncomfortable to write, like really locked down. Like building a jar is like so super solid. So now that stuff is really solid, and we're having fun applying it.
Yeah, it's cool too because like. Maybe it was kind of hard to see because we did some very basic tasks now, but like all the ClojureScript tasks and stuff are doing a lot of kind of complicated things, like all the stuff that Figwheel is doing and all that. But it does it with small tasks that only do one thing. And what's interesting to notice about like how it comes out in Boot is that none of the tasks, they need hardly any configuration, and the reason is because they all communicate through this file set object. Just like in a Ring application, middleware needs very little configuration usually because they figure out what they need to know from the request map or the response map. So a lot of times Ring middleware, you can compose them without needing to, specify where this file, like where is your CSS file. Like it can find it. It says like, look, let me look through the file set, and if it ends with .css, well then that's a CSS file. Or if it ends in .scss, I'm going to make it into a CSS file or whatever. So one of the things that we've noticed with Boot is that we can make all these tasks and we can compose them together without needing to couple them via configuration. In other words, we don't have to tell like this one task to do a special thing so that it works with this other task. Like they just emit things into the file set, and that's like the lingua franca of, you know, how they communicate.
Any other questions? Well, thank you for this this presentation, this interactive demo. Fantastic stuff. Can we thank our presenters? This is great stuff, and I think we're going to see a lot more of it in the closure world in the months to come.
Yeah, this is the you guys are in the you know, the birthplace of Lisp, right?
Yeah, we're on the ground floor.
Honored. That's our motto. Lisp can do it.
All right.
Thank you.
Thank you.
Well, thanks a lot, guys.
Okay.